So today we're going to discuss about the hybrid electric vehicle system. So the content will include how we understand about the hybrid energy source and ICE motor, supercapacitor, fuel cell, and capacitor energy storage system. So firstly, I'd like to ask you about some target question. So what do you know anything about hybrid electric vehicle? What will be the major part consist in the hybrid electric vehicle? Besides motor, battery, what else component will be there? What's the difference between the hybrid electric and motor electric vehicle? So why hybrid vehicle could be perform better than gasoline vehicle? Do you think it will be even better than EV? So some people saying that hybrid electric could be an interim solution to green vehicle. Do you think it only become a transition vehicle? Could it be a long-term or permanent development for future vehicle? What do you think about electric vehicle after 10 years? So beside the gasoline-based hybrid electric vehicle, what other hybrid vehicle would be now available? So think about that. So today we're going to discuss about a number of content, including the series hybrid, parallel hybrid, and series parallel hybrid, which are a combination of the previous two. And then we also talk about some commercial hybrid electric, and also talk about the supercapacitor vehicle, and how are we going to compare the supercapacitor with the battery vehicle. And we're also looking at different type of the hybrid electric vehicle. And also power regeneration is something quite important for hybrid electric vehicle, especially those with the fuel cell. And then we're looking into the conclusion and then final comment. So hybrid electric vehicle actually is simply a combination between the electric vehicle and the gasoline vehicle. So the component key development, including all these parts, including inverter, and also series hybrid, parallel hybrid, series parallel hybrid, important topic. So that means hybrid vehicle actually have been really popular since EV has been launched. You see, initially when we launched the EV, we found that the battery is not that capable. So that's why we tend to combine the gasoline vehicle together with the battery motor vehicle. So in this case, we can able to have compromise. So instead of purely depend on the gasoline, we also want to have some charging, also using the battery, means the battery capability to power the motor, because motor performance really good, have a high instant torque, and also have a really high efficiency. So that's why we tend to combine the advantage of the gasoline IC engine together with the motor. So one thing you can see that hybrid vehicle able to prolong the traveling distance because we make use of the motor, the traveling distance can be similar to the battery vehicle. You can also make use of the gasoline, which is able to provide high energy density of the energy source. So that's why you can make the battery much could be better because battery do have limited energy storage due to the battery energy density. And of course, chemical fuel like gasoline should have a higher energy density anyway as compared to battery. And then we're also looking into power regeneration. Whenever we use motor, we are able to capture the waste energy and then return back to the battery. So that means for hybrid electric vehicle, we do have a battery for the energy capturing during the braking and deceleration. Of course, using hybrid electric, you can turn off the ICE or turn off the motor when the vehicle is idling. So that's the key observation you can see from hybrid electric. So there's a number of combination of hybrid electric vehicle, including a battery combined with ICE. You can also battery combine ICE together with plug-in, so we can charge the battery inside. You can purely have the battery plus the fuel cell. And of course, once we do that, we can also plug in the AC power to charge the battery. And then some other design will have the battery together with our engine, like the IC engine. You also have a full battery system plus a battery. Full battery is another technology we use the electrolyte for the energy storage. So we can exchange the electrolyte, we can use it to fill up the battery vehicle. Not the really battery vehicle, full battery vehicle. But we can also see that supercapacitor is another alternative. So we also look into how the supercapacitor can become a hybrid vehicle combined with the battery. So for different kind of hybrid, one thing you can see that our popular one is so-called the series hybrid. You see, series hybrid basically will be connect the field to the wheel in series manner. So the field will pass through the ICE, and there is a generator produce electricity. That electricity will charge in the battery, and everything will pass through a battery anyway. The battery energy will therefore discharge through the inverter to control the motor. So that's why you can see that here will be hybrid. Battery will be 10, will become a buffer to decouple the ICE and both the motor. So that's to say we don't need to worry too much about the motor power, how that relate to ICE or vice versa, because they all separate using the battery as a decoupler, decouple these two. So you can see that the design could be simple. We don't need to worry about the torque control from the ICE and the motor because they're separate control. We only need to design the torque control for the motor. That's it. And overall design will be straightforward, easy to design. It's also good for the ventral fitting. That means if a battery vehicle, you can install the gas generator, then it will become a series hybrid. So there's a number of operations for the series hybrid, including the battery charging mode. So you can see that we use the fuel, ICE fuel, to charge the battery. So that especially useful when vehicle under idling. And then another one is hybrid motoring. So that's to say the whole connection is in operation. So besides the fuel charging a battery, the battery also use it to power the motor. So in this case, the fuel is discharging to the motor. Another thing will be the discharging motoring. So in this case, the fuel IC is being turned off. Only the battery power up the inverter and motor drive. Another operation is power regeneration. So that means ICE will be idling or turned off. And then the motor, if you're going down the hill, the vehicle that are going down the hill, the dynamic energy will return through the motor to the battery. In this case, the motor becomes a generator. So another is parallel hybrid. Parallel hybrid means the ICE and also the motor will connect mechanically in parallel to the wheel. So in this case, both of them control the mechanical power, and the torque control in here will be need more dedicated control manner. So the output power, of course, will summation of motor, electrical motor, and ICE. So usually they can be high power, powerful, experienced during the sensing, acceleration, or overtaking. So, but the charging of battery cannot be done straight away. Must be through the ICE, through the IC connection to the motor, now become generator to charge the battery. Can only through this part. So let's see a number of operations. Firstly, will be the field discharging. So the field will discharge its energy through the ICE to charge the motor. Another one will be its operation. So both of them, the battery control motor because of mechanical power, and field control IC because of mechanical power, both of them add together to the wheel. So that's a really common mode because hybrid electric is a parallel mode. We can make use of power for either motor and also ICE. So that means you can increase the total power of the driving. And power regeneration mode, that means the wheel when go down the hill or stopping deceleration, you can return energy through the motor to the battery. In this case, the motor become a generator. You see a motor generator, they are interchangeable. All the motor can become generator. All the generator mostly can become a motor anyway. So battery charging mode will be when the vehicle stand by, we can use the clutch to disable the wheel from the connection to the ICE. ICE just focus its power through the generator to charge up the battery. Then of course the battery charging mode will be mean the battery now discharges energy to power up the motor to drive the vehicle. In this case, ICE will be more like stationary. So all of them usually we like to have a plug-in hybrid. That means because the battery is in the vehicle, then sometimes if we don't want any emission, we want the 100% electric, then we can use onboard charger to use plug-in method to charge the battery. In this case, the battery need to have a slightly bigger size so that we're able to accommodate more energy content for the onboard charging. So that means this kind of the plug-in hybrid, usually the battery will be 1 time or 2 times, maybe 3 times bigger size than the conventional hybrid. So, but to design this system, not that easy as compared to series hybrid because it do relate to the torque control, how to manipulate this motor and ICE together to control the wheel. Then another combination will be we connect the parallel hybrid and series hybrid together. So to get the advantage of both of them. In this case, you can see that ICE and the motor both parallelly to drive the wheel. But however, we have a separate generator. We connect ICE for the generator to charge the battery. In this case, we look like series parallel together of operation. So there's a number of mode of operation. Firstly, would be the fuel discharge. The fuel discharge from the chemical fuel through the ICE and then power up the motor. Another one is hybrid motoring. So that means motor get the power from the battery and power up the wheel simultaneously. Then we also get the power from the ICE. And sometimes we also need to provide power from the ICE to drive the wheel. And then simultaneously, we use it as a power to charge up the battery. Then power regeneration means the wheel going down the hill or stop in the traffic light or wherever it stops, you can return dynamic energy through the motor to the battery. So another would be hybrid motoring and charging mode. You can see that all the items are connecting. So IC is now connected to the wheel, and the motor also connected to the wheel simultaneously. IC also power up the generator to provide power, charging power to the battery. So you can see that there's a number of operations. Actually, there could be more operation. Then you can think of any other operation. So in the market, I think total periods is one of the popular ones. So it launched in 1997, and then still one of the best seller for all the hybrid because it's a long history of development, really good record. The engine size is about 1.5 to 1.8. A typical mile per gallon will be 42 to 56. That's a really good, better than many other vehicles, a few times compared to other vehicles. The weight for the vehicle in the curbside is 1 ton something. The top speed is 112. So battery inside means this kind of the battery inside, they still using nickel metal hydride at some time because when they first developed, the nickel metal hydride is the available battery. The battery is not very big, about 6.5 amp, small battery, quite a small compartment, about that kind of size. The voltage, not very high, about 200 volt. So we can able to use system voltage 650 anyway. So this vehicle is called the series parallel hybrid. So in the market, there's a number of different kinds of the hybrid, like Escape hybrid from Ford. So the top speed 164, and the plug-in battery, plug-in charging will be 14.4. Another one will be 42 miles per gallon from Friction hybrid. So the motor will be 88 kilowatt, and the energy storage is quite small, 1.4 kilowatt hour. So probably that may not be enough for all the opportunity or all the application, but because that is not using plug-in charging anyway. So however, the plug-in version, the battery size will be much higher. You can see that 9 kilowatt hour, and the range will be probably slightly higher. So another section where we discuss will be about the super-capacitor. You see, super-capacitor, another type of hybrid, another type of energy storage, similar to battery, but however, it's more capable with the battery because its energy content will be much lower, but the power will be much higher. You are able to have a really high power charging, maybe a few times higher than normal. And then like this vehicle design, it's a bus company. The top speed only 55 km, only testing. The fully charged, probably 20 minutes will be sufficient because it's used supercapacitor, the charging speed is really, really fast, but you can only charge for 20 to 30 km. The cost also quite expensive during that time. I think they may have subsidy from the government. They are at the pricing of 0.3 million. So the concept of supercapacitor is that we are able to use capacitor as energy storage because lifetime is good. So that's why you can use for many, many years. Even though the vehicle be retired, we can still able to use the capacitor. So we tend to use supercapacitor. In this case, we use capacitor to replace the battery. Anything about the battery no good, usually the supercapacitor able to perform better to replace them. So the background would be like that. A capacitor-based vehicle would have a quite good advantage because we don't need to depend on chemical reaction. We just use electrostatic or electro method to develop the charge inside. But of course, the charger also quite special because we're charging supercapacitor, the power could be quite high because we're talking about the duration of charging could be much reduced because high C rate. So the power level for the charger could be increasing. So the capacitor energy is a high speed. You're able to provide high speed energy to the motor drive. In this case, that will facilitate the propulsion. So high current, high power drive to do that. So here is a typical schematic of a supercapacitor vehicle. You see in this box here, usually with battery, we can just replace them as a supercapacitor. Then we have plug-in charger to charge the supercapacitor. The other thing was motor drive and also power regeneration control system. So when we have the plug-in power, we charge the battery, the supercapacitor. The supercapacitor can therefore power up the motor and vice versa. So for environmental point of view, you see, battery is not that environmental friendly because some of the battery consider lead acid. The lifetime is not really promising, 1 year, 1 year plus. For lithium ion, the lifespan is only 5 to 7 years. So, but you can see that recycling of battery is difficult. Today, most of battery, they are very good in dealing with the manufacturing, but recycle the battery could be a lot hassle because the technology is not there. And many of the chemical can bond to other material, we have difficulty to take out. And also battery could suffer from explosion, although we don't have that many cases nowadays. But in the 5, 10, maybe 15 years ago, we usually hear about the lithium ion battery get explosion or on fire. So that means there's something, if we use the supercapacitor vehicle, we don't have this kind of issue. We don't have this kind of the lithium ion battery issue anyway. So issue of the battery, including if we use lead-acid battery, the old type of battery, so-called star battery, then we highly toxic. Many people don't like that. Even though we dispose battery, it's not very convenient. And so for the recycling battery, also issue. There's no government like to accept your used battery because they all consider as a waste. So that's another issue as well. And today we got many appliances based on battery type, including powerful energy storage or building, electric vessel, electric aircraft. We also use energy storage. So I guess in the future, the power demand could be quite high. We may not have sufficient lithium able to provide for this application. So however, we can see the main advantage for supercapacitor will be the capacitor base. So it's not chemical based. We don't have any chemical energy. You're all using energy storage, electrical energy storage. And also rapid charging and the charging of a capacitor. It's not a simple job. Capacitor usually based on the high capacitance value or low voltage value. In this case, that will increase the energy density for the capacitor energy storage. So the important point we look into the capacitor vehicle will be, we don't need to worry about any heavy metal. Like the battery, we usually consider heavy metal, but supercapacitor only electrolyte, usually with some plastic base, and most of the terminal. So we don't have any concern to the heavy metal in supercapacitor anyway. And supercapacitor, because you don't have any metal component, don't have third wire, don't have 11 wire. In this case, you can able to meet with some strange environment, especially wire temperature range. You can, because capacitor, you don't worry too much about the magnetic field inside. So the temperature usually quite wide range from 0 to 60 or maybe 80 degrees, also maybe even higher, also become possible. So you also have opportunity of higher energy density because we can see that for research at the moment, we can see a big improvement for supercapacitor. Hopefully after half a year, then we can able to improve further. So other advantage including is based on static charging, not dynamic charging. So that means the charging rate could be really fast. We have lower if cycle. The issue is supercapacitor. Normal lithium ion, we cannot discharge to 0%, otherwise you totally damage. A supercapacitor only electronic device, even though we discharge to 0, there won't be any problem. Of course, we don't usually discharge to 0, because 0, because a square relationship, the power don't have that much anyway. And for the rapid charging, lithium ion battery do have a rapid charging issue. However, for this kind of capacitor, we don't have anything like that. So capacitor actually offer a lot of the advantage, including power, lifespan, and deep cycle. That's why people start to look into supercapacitor to see if there will be a good opportunity to use supercapacitor as energy storage for EV. But however, you can see that we've been talking about supercapacitor for quite some time. Why still not that popular? I think mainly about a lot of the issue. One thing would be about the distance, traveling distance. Although we can able to reduce the charging time by using high current to charge the supercapacitor, but the power demand, power electronic circuits for supercapacitor could be very large if you use such a high current. If we reduce the current, then we don't have sufficient advantage as compared to gasoline or compared to battery vehicle. So high power circuit for charger is something we don't quite want because the electronic, the transformer, the substation requirement could be very high. So today we're already using the power electronic technology to develop this high power, high density, high efficiency anyway. So because of high current, high power, we're also using some new technique called the zero current switching to reduce the current. That to say zero current switching is to reduce the charge, the overlapping between voltage and current in the switching. We use soft method to reduce the current. So here we, again, here we try to compare the supercapacitor and battery. You can see that capacitor-based vehicle could allow the very fast speed of the charging. So although energy density of a battery is much higher than the capacitor, then of course, but however, capacitor do have much higher power. The key disadvantage will be just energy density is not as good as battery. We usually, when we use a supercapacitor vehicle, we only use roughly just a few percent as compared to the battery vehicle. So another advantage, you can see that we can, there's a lot of development in supercapacitor or ultra capacitor. So you see, since every year there will be improvement in the energy storage. So probably after a few years, we can see a much higher way to operate on the supercapacitor. You can able to reduce the cost and we improve the energy density so that you can able to more compatible to the battery vehicle. So here will be some comparison compared to the major battery system, like the lead acid battery. You can see that lead acid battery, the WH per kilogram, the energy density used about 35. Lithium can be 140. If your NMC battery can be up to 200. But look at the supercapacitor. You can only have 4.6 WH per kilogram. So compared to lithium battery, I think it's just more than 20 times of difference. But so that's why although we think supercapacitor good, but for large scale energy storage may not be highly suitable because of the price and the rate. To compare the conventional battery, conventional battery don't have that capability. You can see that conventional battery, the energy density, WH per kilogram, only very small, 0.015 anyway, compared to 0.6. So it's a quite big difference. For energy content for supercapacitor, we can use capacitor energy equation half CV squared and to estimate the SOC, because there's a strict simple equation half CV squared to get the energy. So we can just measure the voltage, then we know the SOC for the battery. Then for the understanding of energy storage, we usually use Coulomb counting. That means how much charge being stored. So initial charge plus the additional charge, then that will give us the kind of the Coulomb counting, simple counting method. But counting may be an issue because Q0 is the initial charge. If the initial charge are cumulative error or other error, then you can not reset properly. So we need some good reference to understand the initial charge. So that means if you use this integration method to get the charge, there may be some integration error or cumulative error that may affect your estimation for the battery energy. So here are simple connection, how we make use of supercapacitor. You can either just connect them in parallel like this. However, some of the application we do have a converter to convert the supercapacitor into a link first. Why we do that? Supercapacitor is really expensive. Usually when each battery cell only about 2.7 volt, even to connect all of them in series, we may not have sufficient voltage as compared to battery. So that's why we need a controller here. Firstly, the controller makes sure that we are able to control the current in here. Secondly, we can also put in a power converter to match these two voltage. These two voltage may not be equal. Once we put a power converter or current mode controller, some power circuitry like that, we can match up these two voltage. Sometimes we need to put two, sometimes we need to put one, depending on our design. So we do have many other type of the hybrid electric. I think what I want will be the future fuel for vehicle should be zero emission. So nowadays I can think of three gas fuel are zero emission, like hydrogen, ammonia, and hydrogen sulfur. So a lot of people has been research on hydrogen vehicle. Then of course ammonia just started. I and my team only started ammonia vehicle recently, and a really good success. We already built the first ammonia powered electric vehicle. Another fuel will be hydrogen sulfur. Also, no carbon there. But hydrogen sulfur have a very strange smell. The smell is not really favorable. And also, very few we hear people use hydrogen sulfur to become energy source because you may deposit sulfur. The sulfur can deposit, become sulfur dioxide. That could be really toxic material. So it seems that ammonia could be quite possible because firstly, you've got high energy density. It's really safe. And also is more look like ammonia will generally produce hydrogen. The hydrogen will be really similar to other fuel cell hydrogen vehicle. We just generate the hydrogen from the ammonia and then use the hydrogen to power the vehicle. So we don't need to store any energy there. So the good thing is if you don't store the hydrogen energy, the vehicle can become safer. So there's many hydrocarbon fuel like methane, ethane, or many other. So you can see that they all conserve carbon. So that's to say, if we try to decompose it using any method, then what we have here, we do have the carbon emission. So how to deal with the carbon emission, other topic. For example, like using the blue method, then we are able to capture the carbon dioxide. So we are also other fuel like here, liquid fuel like ethanol, all this thing, or they are not quite suitable for our application either anyway, although they do have high energy density. Sulfur, hydrogen sulfur all have disadvantage because it's flammable, very easy to catch fire, and also limited energy density. And sulfur still have a low energy density compared to other fuel. So why don't we start to have other fuel, have zero emission first? Residue. The hydrogen sulfur, the residue may form some kind of the yellowish powder like the sulfur dioxide. So it's also highly toxic and sometimes can be acidic because once this kind of sulfur dioxide, when it mixes with water, become become sulfuric acid, that will be strong acid. So that may need to have further discussion or further management, how to use the sulfur dioxide. At the moment, we see that, but we still didn't see any development. So toxicity, we don't like toxic. So that means we try to eliminate hydrogen sulfur. Hydrogen sulfur is those smelly things, like what we hear in the rotten egg or in the toilet, public toilet. Also, corrosion is something we need to look into. Hydrogen sulfur is highly corrosive. So if in touch with other material, it may cause certain damage. So we do need to be careful for that. So another thing I want to explain to you will be ammonia fuel cell vehicle. Ammonia fuel cell vehicle mainly to use the ammonia to crack them into hydrogen, and use hydrogen pass through the fuel cell to power the vehicle. It's a more logical because we don't want to carry a high gas tank of hydrogen that's dangerous, and density will be low unless we pressurize them to 700 bar, but that will be a lot of the effort, a lot of the investment. But using ammonia, we can crack the ammonia in the hydrogen. The hydrogen can therefore power up the fuel cell and then the vehicle. So, but however, you can see that the transition from ammonia to LPG could be quite possible because they all operate at low pressure. LPG gas pressure roughly about 10 bar, ammonia also 8 bar, so they are pretty much similar to each other. Then we have high confidence we are able to launch the ammonia vehicle. But however, we don't have existing infrastructure for ammonia. We still need time to build, even though that existing structure of hydrogen is still not yet mature, so we still need more time to build. Energy density of ammonia much higher. In theory, we get 50% more energy, more hydrogen as compared to hydrogen gas. So that's why we do prefer to use ammonia as the gas fuel as compared to hydrogen anyway, because we got 50% more. For the storage, I think storage for ammonia only 8 bar, that will really much comfortable. But the storage for hydrogen is not simple. Most of them, they have international standard for 700 bar or 350 bar. And then ammonia can be also used renewable to generate. For instance, we use solar power, wind power, which renewable energy to produce electricity to use this method to generate ammonia. So firstly, we use this method to generate hydrogen from water. And hydrogen can combine it with nitrogen, become ammonia. So this is one of the green methods we have been using. So that's why beside hydrogen have a different color, actually ammonia can also have a different color. But what I want in the future will be, I don't want to synthesize the ammonia. I want to use natural resources to capture as much as ammonia possible. So by doing this one, we can able to reduce the greenhouse gas emission because we no longer depend on ammonia. So that means using ammonia as a fuel production, and that could be a lot of opportunity. So tutorial. Let's see how to design a supercapacitor car. So assuming the energy storage will be 120 kWh for a vehicle, which is a combination of battery and supercapacitor. You know, we cannot put too much supercapacitor because too expensive, too heavy. Assume we only use 2% of supercapacitor. So, and then supercapacitor, the voltage 2.7 volt, not really high voltage. So that means we usually use a number of them in series to make up the requirement of DC link voltage. Now that the DC link voltage is 540, you can see how we do the calculation later on. Then the supercapacitor, if we use 300 F of supercapacitor, so can you recommend the supercapacitor connection? How many in series, how many in parallel? So if each supercapacitor can supply 100 amp, what will be the total current you can able to supply to the inverter? So that's simply to see how many of them in parallel, right? If the real current of 100 amp of each supercapacitor, then what is the C ratio of supercapacitor? So C ratio is something we want for all the energy storage, yeah? For if we get battery portion, only one C, what is total C ratio for the whole energy storage system? Okay, let's see the answer. So firstly, we want to calculate the configuration, how many in parallel series. We got 120 kilowatt hour, 2% will be supercapacitor. So 2.4 kilowatt will be the supercapacitor. So we use half CV squared to calculate. So we need this 2.4 kilo-hour, and then the voltage of supercapacitor 2.7 volt anyway. And then the capacitance usually 3,000 every one the standard. So we can use this method, half CV squared. We can calculate energy density for supercapacitor. So that means for this configuration of energy storage, then individual supercapacitor, we know how much it is. So we can divide total energy content by individual supercapacitor energy content, happen to be 790. Of course, we choose a whole number, 800. So 800 will therefore equivalent to how many parallel, how many series? Now, we got total voltage about 540 volt. And then if we divide by 2.7, we see that we need 200 of them in series. If 200 of them in series, total number with 800, obviously need 4 in parallel. So that means each supercapacitor able to provide 100 amp, and then because 4 in parallel, total current supply can be 400 amp as a maximum. So energy storage for the supercapacitor 2.4 kilowatt divided by voltage. And then that means the mH for the supercapacitor unit would be 4.44 AH. So we sometimes when we analyze supercapacitor, you usually think about consider the parameter we use for the battery anyway. So that's why we still have the AH voltage kilowatt-hour anyway. The rated current in 100 amp with 4 in parallel. So that's why rated current need to multiply by 4. It represents 4 in parallel, each 100 amp. So the C rate will be 400 divided by PVC 4.44 energy density give me as 90. So that means this kind of arrangement, the supercapacitor has a high C rate up to 90. You see, just previously I mentioned about 100, so it's close enough. So if the battery energy efficiency will be 98%, 120 kilo-hour, the actually energy you can able to obtain will be 117 anyway. So with this energy content divided by 550 volt, so the equivalent to the battery energy will be 217 AH. Now then, these two are connected in parallel. Yeah. So that is to say, we got 120 kilowatt, and then we divide by 540 volt. So that is how we see the whole system, combination of battery and supercapacitor. The AH value will be 222. Then if we try to compare the whole system, after we have supercapacitor and battery, with supercapacitor 400 amp, and just like we calculate the battery only at 217 amp for the operation. So this will give us 2.78. That you see this combination of battery and supercapacitor, you can therefore have something related to 2.78 of the C rate. So about 1.78 better than the other C rate. So next thing is to see how we comment to the supercapacitor design. You see, supercapacitor design actually, although we think capacitor can able to vary the voltage from 0 volt to 2.7 volt, but do we usually only discharge to 0 volt? Probably may not. We usually only discharge half of original voltage. So that means 2.7 divided by 2, 1.35. Why is that? Although supercapacitor don't have any issue to reduce to 0 volt, however, to boost up the voltage from 0 volt to use its energy at low voltage will be not convenient. 2.7 is easier to attract its voltage, attract its energy. But however, we usually only reduce the voltage to about half of 2.7 so that this voltage will be more sensible to convert its energy back to the load. So that means using half CV squared, we can calculate when we reduce from 2.7 volt to 1.35 volt, what is the variation of energy? So calculation will be 75%. So that means if we reduce the batch to supercapacitor to half its voltage, the total energy we can able to obtain from there will be only 75% rather than 100%. But still 75% is better than the battery system or battery vehicle system. But because supercapacitor is expensive, so that's why we do not afford to have a large amount of supercapacitor anyway. Supercapacitor usually connect in parallel, or it only represent a small portion of total energy because of the cost of supercapacitor. Next thing, we can compare the hydrogen fuel cell vehicle with the hybrid electric. So let's just see an example. If we design fuel cell hybrid electric using hydrogen fuel cell and lithium, then you can see the range is 600 km. The average power demand will be 25 kilowatt. Just one example for the vehicle. The top speed 160 km per hour. The regenerated power efficiency only 13%. That means you only capture 13% of the energy during braking, or only 30% energy can be recovered during the motoring journey. So that's what we're trying to say here. So now then, given the data will be energy density for hydrogen will be 33.3 kilowatt per hour. So this so-called the low heating range, more energy will be inside the hydrogen. For fuel cell efficiency, usually can be 50%, 60%, we use 50% here. The lithium battery specification, so we are trying to use 150 kWh per kilogram is very reasonable. The efficiency 90%. The depth of the charge will only cater to only 80% anyway. The vehicle mass is 1.8 ton. So let's see the calculation. So you can see that assume the fuel cell can provide 70% of total energy and 30% will be from the battery. So because we still need some battery energy because of power regeneration. So that means the energy required for 600 km will be like that 600 divided by 160 km per hour. Then give us the time of traveling. Then that will 25 kilowatt times the time. Then we get 97 kilowatt hour. So that's the energy required for 600 km of the traveling. But the efficiency for fuel cell only about 70%. So that means multiplied by 70 will give us 65 kilowatt hour. Then for the fuel cell, hydrogen fuel cell. So we demand this energy from the fuel cell. Efficiency of fuel cell only 50%. So we divide by 50 will give us 131 kilowatt hour for the fuel cell. So this kind of the energy, because the performance for the hydrogen fuel cell only give you 33 kilowatt hour per kilogram anyway. So this division will give us the requirement for hydrogen for this operation will be 3.94 kilogram of hydrogen to fulfill that operation. So for battery sizing, the battery just now will be about, we can calculate using 30% of battery ratio in that design, 70 go to fuel cell, 30% go to the battery. In this case, for multiplication, will give us 28 kilowatt hour for the battery requirement. So that will power regeneration. We assume 30% of energy can be recovered. So for the 93 kilowatt hour, 30% can be recovered. That means we got 12 kilowatt hour for energy can be recovered. So that means the actual battery requirement, or we calculate 28, but actually 12 kilowatt can be recovered. So minus 20, 12 become 15.9 kilowatt hour. So actual energy requirement only 15 kilowatt hour. So 15 kilowatt hour, you can check this mass of the battery can be used. So we can divide it by its energy density, and then also divide by 80%, you give us 132 kilogram. So we need to use 132 kilogram for the lithium-ion battery. So you can see that now the hydrogen energy and the battery energy after loss will be like that. 131 plus 15.9, but using 90% efficiency, will give a total energy will be 148 kWh. So you can see that if you use pure fuel cell to manage the whole 93 kWh, then we require 187 anyway. So that means the improvement will be like that. 187 minus this 148 and divide by 187 will give you 20%. So that is to say, using this method, we got 20% high efficiency using the hybrid method. So that's still an improvement, but not very big, but also an improvement. Next section, power regeneration for braking. You see a hybrid electric vehicle, if you're using purely fuel cell don't have any power regeneration capability. We can't using electricity to charge the fuel cell, impossible. So that's why we need to have a secondary battery for it there, maybe in parallel with the DC link to absorb the power regeneration due to the vehicle braking or maybe reducing the speed. So the key reason is fuel cell only unidirectional, can only give away the power, cannot power regen. So that's why we do need the battery. So do need to remember that. So that's why the battery main thing in here will be have a buffer to buffer energy from the fuel cell to the motor, and also buffer energy as a kind of tolerance in case any inconsistent in the input, we still have battery to make the system stable. And battery usually nowadays is very stable system, very stable current, stable power, stable voltage, can be done really well. But the thing is to recover, how much energy can recover from the whole journey? Or depending on the journey, depending on EV, usually can be from 10% to 70% of the journey can recover. It all depends on many, many factors. So that means that can really have a good impact to increase the range in the city driving. So to conclude what we learned today, we discussed about the battery and the capacitor-based energy storage for electric vehicle and also hybrid electric. Usually, we try to combine the ICE with the electric motor in the hybrid electric. So people will say hybrid electric could be an interim solution because I think in the future, EV can do it much, much better. We don't need any gasoline inside vehicle anymore. So capacitor and battery system are now being used for EV and maybe hybrid electric. But I think in the future, we think that battery is something good, but it may able to power up the electric vehicle with high power solution. But for supercapacitor, you can able to provide even higher power solution. Maybe super fast charging also be possible by using supercapacitor. So that means how we combine them is something future design we need to look into. So thanks for the supercapacitor now become more feasible for capacitor battery-based vehicle. You can make use of advantage for supercapacitor and battery and combine them together. So in this case, we can able to reduce the long charging time because supercapacitor able to charge really, really fast. So finally, you can see the final comment will be supercapacitor actually face a number of challenges. Firstly, will be about the energy density, not as good as the battery, still 10 times, maybe more than 10 times, 20 times as compared to the battery. But another thing will be the cost, really expensive. So if we use a supercapacitor vehicle, even though you use small 5%, I feel low percent still really expensive. So that means existing application, we tend to use supercapacitor for those conditions. That means we have frequent stop. So when stop, we charge the vehicle. We use this so-called opportunity charging. And the battery only for long range, probably for the outside city, then use a supercapacitor. Inside city, you can use, outside city, you use battery. Inside city, you can use supercapacitor. For industrial use, sometimes we use supercapacitor because it's rapid power, rapid charge and discharge. So in some way, it can be suitable for some crane or some elevator, then we are able to use it for this market. So the future outlook will be, we are all looking into zero carbon mobility. And so that means using gasoline may not be a long-term solution. Only hydrogen, ammonia could be a long-term, a good solution anyway. The infrastructure is something we need to look into. Usually, battery plus supercapacitor could dominate the fast charging network because we can make use supercapacitor is high power capability, although we use small percentage. But just now the calculation, you can see that even though we use very small percentage, 1%, 2%, we can still helping the C wave for the overall structure. Hybrid electric may be an interim solution or may not, because people like to have hybrid electric because you can able to have a long duration of operation. You can quickly to charge it, fill up the fuel, then become a long range of the driving. So, however, we still need a lot of innovation for the supercapacitor fuel cell, able to prolong its operation, reduce the cost, improve the market, improve the operation. So now then we need to think about how we can promote all this, like can we have a hybrid technology to accelerate the R&D technology in the fuel cell vehicle. So fuel cell vehicle still have a problem nowadays. After we study for quite some time, we still have a difficulty for commercial adoption because still supercapacitor is still really expensive. Although we know there's an improvement, but still we need a more rapid solution anyway. So supercapacitor still need to work together with a battery vehicle really well. Without both of them together, it's really difficult to become a supercapacitor vehicle. So that's all from me. So that's the reference. You can take care of it. Thank you.